Hi all, I hope you are doing fine. So this is continuation of RMP part 3. Those who haven't watched part 1 and part 2, I'll provide the link in the description. You guys can see from there. So let's begin the topic. In the previous video, as we discussed that K plus, it begins to move down its concentration gradient, that is outside of the cell. So basically, due to movement of these K plus down their concentration gradient, it creates a charge imbalance across the membrane. And this charge imbalance, it opposes the flow of K plus down the concentration gradient. We also talked about the electrical gradient that developed inside the cell and how this electrical gradient got stronger progressively with time due to more diffusion of K plus outside. Let's suppose we have a concentration gradient of 5 initially, and an electrical gradient of 1 is opposing it. With time, with more diffusion of K plus, what is going to happen is the concentration gradient, it does not change much, it is still 5. But this electrical gradient, it gets stronger over time due to the charge imbalance created across the membrane. And as I told you earlier, that K plus is associated with its anions inside. So whenever a K plus leaves the cell, it leaves behind an unoccupied anion that is negatively charged. So what is happening is as more and more K plus it diffuses out of the cell, it becomes really difficult for the remaining K plus to go out. Why so? Because every time this K plus diffuses out, it leaves behind an unoccupied anion. And as anion is negatively charged, these remaining K plus, they are strongly attracted by these anions, which makes it really difficult for them to leave the cell. Now look at another situation. Let's suppose significant amount of K plus has diffused out, producing more and more electronegativity inside the cell and more diffusion potential. There comes a time when concentration gradient that is acting outwards become exactly equal to electrical gradient which is acting inwards. Now if concentration gradient is 5, this has also become 5. So what will happen at equilibrium, there will be no net movement of K plus. Despite of the fact that membrane is still permeable for K plus, there will be no net movement of K plus across the membrane because the concentration gradient which was taking K plus outwards has become exactly equal to electrical gradient which was holding it inwards. Basically, what does no net movement of K plus means actually? It means that the number of K plus that are going out under the concentration gradient are absolutely equal to the number of ions of K plus which is coming in under the influence of electrical gradient. So this chemical gradient or concentration gradient that is moving the K plus outwards and the electrical gradient that is holding the K plus in has become absolutely equal. Now see, let me give you a quick review. As K plus started going out, it developed electronegativity inside the cell. Let's say from -5 to -15 to -25 to -50. Alright, so this electronegativity was developed due to diffusion of potassium. We say these are potassium diffusion potentials. Alright, as more and more K plus goes out, K plus diffusion potential becomes more and more in its value. A time comes when diffusion potential of K plus it becomes equal to the concentration gradient. Diffusion potential of K plus it becomes strong enough to oppose exactly the concentration or chemical gradient. That is, it stops the net movement of K plus and we say that K plus has achieved an equilibrium between its concentration and electrical gradient. So that potential at which equilibrium is achieved is called equilibrium potential. Or in right words, we should say that membrane has achieved equilibrium potential for potassium. Now guys, I'm sure you must have heard another name for equilibrium potential, that is Nernst potential. See, Nernst potential is nothing but the equilibrium potential for the ion, right? So what is Nernst potential for the potassium? That is, it is the equilibrium potential for the potassium. And what is equilibrium potential? It is the diffusion potential of the potassium at which the net movement of the K plus is 0 in spite of the fact that membrane is fully permeable to K plus. Now let's see the gradients. If you look at the concentration of K plus outside, it is 4 milliequivalent per liter. And if you look at the concentration of K plus inside, it is near about 140 milliequivalent per liter. Also, if you take the ratio of K plus inside to K plus outside, it is about 35 is to 1. So what I'm trying to convey is at these concentration gradients, that is when outside is 4 and inside is 140, the Nernst potential for potassium, it is at about minus 85 millivolt. See the RMP, it holds a value of minus 90 millivolt. And we started right off from minus 5 millivolt, which was generated by electrogenic sodium potassium pump, and from minus 5 millivolt to minus 85 millivolt. Okay, so this has been generated purely by the diffusion out of K plus. Now, basically, this is our first hypothetical cell where the membrane was just permeable to potassium. And now we'll talk about another hypothetical cell where we'll see what happens if membrane is only permeable for sodium. This is our second hypothetical cell where the cell membrane is just permeable to sodium, not potassium. And just like the previous one, this cell also has this sodium potassium ATPase gene, which is making these sodium potassium ATPases. And as we know that sodium potassium ATPases, in turn, they are accumulating lots of sodium outside, that is extracellular fluid is rich in sodium and it is concentrating potassium inside, right? And it's an electrogenic pump, that is loss of cations is more and gain of cations is less. So inside of the cell, it is becoming electronegative and it produces electronegativity of about minus 5 millivolt. This is by sodium potassium ATPases, as we know. See, this is what we have already studied in detail in the previous videos. All these things, they are common in both the cells, but the thing which is different is, as I said, that the membrane, the cell membrane of this second hypothetical cell is only permeable for sodium. It is not permeable for potassium. Why so? Because the gene which is responsible for making channels for potassium is not working. Only the gene which is responsible for making sodium channels is on, and this one is off by chance. So due to activity of this gene, we are going to have sodium channels here. All right. The only difference between the first cell, which we discussed, see this one, and the second cell, which we are discussing, is that the first one, the cell membrane, it was permeable for potassium, not sodium. This one, the cell membrane is permeable for sodium, not potassium. So now let's see what happens, as we already know that sodium has a higher concentration outside and it is less inside. So this sodium, it would actually love to go inside if the membrane is permeable, and of course the membrane is permeable to sodium. See, in the beginning, concentration gradient for sodium is towards inside because sodium is more outside and it is less inside, and as we all know that substances move from their higher concentration to their lower concentration, so this sodium, it would love to go in. See, the concentration gradient for sodium is inwards, but what about electrical gradient? In the beginning, it is minus 5 millivolt. So due to this minus 5 millivolt, a little bit of electrical gradient is also acting inwards due to this minus 5 millivolt. So initially, as we can see, concentration gradient and electrical gradient, both are acting inwards. Both electromotive forces are helping this sodium to go inside. And guess what? Sodium happily moves inside. When this sodium, it comes inside, guess what happens? Electronegativity of the cell is neutralized. Why so? Because cell is now gaining cation. So sodium, under the influence of its powerful concentration gradient, it moves inside the cell and electronegativity of the cell is lost, and guess what? It becomes absolutely zero. Electronegativity of the cell becomes zero. Now when the electronegativity has become zero, do you think any more sodium will come inside the cell under the influence of electronegativity or this electrical gradient? Because the electronegativity is lost, right? So no. But don't be sad. Our sodium is very determined. It will still come in. Why so? Why will sodium still come in? Why? Because concentration gradient is powerful. It is powerful enough even though we don't have any electrical gradient now, but the concentration gradient is so powerful that it still drives the sodium inside the cell. So some more sodium comes in, and due to that what happens inside of the cell will become electropositive, let's say plus 10 millivolt. So sodium, it will keep on coming in under the concentration gradient power, and inside of the cell it will become progressively more and more electropositive. Let's say plus 20, plus 30. Alright, so now what is really happening is, now see this sodium, this is pulled in by concentration gradient. And as inside of cell is becoming progressively more electropositive, this electropositivity will repel it. That is, electrical gradient will push it outwards. See, this electrical gradient does not want sodium to come in. It is acting against the concentration gradient. But this sodium, it still comes in. Why so? Because concentration gradient is strong. Alright, so due to that, sodium keeps on coming in, and inside of the cell is becoming more and more electropositive. So we say that diffusion in of the sodium ions is producing what? That is diffusion potential for sodium. See, what is diffusing across the membrane? This sodium, right? So we say that membrane is producing diffusion potential for which ion? That is sodium. Now, see, when cell membrane is permeable to sodium, because of its concentration gradient, sodium rushes in. Because outside it has a higher concentration, so it's going to move from outside to inside. Then what happens? Sodium diffuses inside, and interior of the cell is becoming progressively more and more electropositive. See, in this particular case, concentration gradient is acting inwards, but electrical gradient is acting outwards. And this electropositivity, plus 10, plus 20, plus 30, which is developing inside the cell, due to diffusion in of sodium, this is called what? Diffusion potential for sodium, or we say that membrane is developing diffusion potential for sodium. Now what's going to happen? See, a time will come that diffusion potential of sodium, this diffusion potential across the membrane, it becomes strong enough to balance what? Concentration gradient, which is acting inwards. And when this is achieved, the concentration gradient, which is acting inwards, and this electrical gradient, which is acting outwards, become absolutely equal, despite of the fact that membrane is still permeable for sodium. At that particular potential, when diffusion potential of the membrane for sodium, it becomes strong enough that it does not allow any more sodium ions to come in. That is, it balances out the concentration gradient. We say membrane has achieved an equilibrium potential. Membrane has achieved an equilibrium potential for sodium. Now, let's look at the gradients for a while. Sodium concentration outside, it is 140 milliequivalent per liter, and sodium concentration inside the cell, it is near about 14 milliequivalent per liter. If you take the ratio sodium outside to sodium inside, this is 10:1. Now what is this ratio 10:1 indicating? See, this ratio 10:1, it is trying to tell us that sodium is 10 times greater outside than inside. So sodium is basically having 10 times gradient to move inside. Alright. So at these concentration gradients, when outside is 140 and inside is 14, if you look at the equilibrium potential or the Nernst potential for sodium, you know what it is? It is plus 65 millivolt. Now what does it mean? Let's get back to the previous slide. Just a second. Yeah, so now see. When sodium, it started coming in under the concentration gradient, inside of the cell progressively became more and more electropositive. And then what happened? Membrane started developing diffusion potential for sodium. How much? Until diffusion potential for sodium becomes plus 65 millivolt inside. Because that is the equilibrium potential, that is the Nernst potential. See, this equilibrium potential plus 65 millivolt is strong enough to oppose the concentration gradient. Basically, it balances out the concentration gradient and does not allow further influx of sodium. What I'm trying to say is at plus 65 millivolt, there will be no net movement of sodium across the membrane. The net movement becomes zero despite of the fact that membrane is still permeable to sodium. Also, when equilibrium potential will be achieved, look at these channels here. They will be open, but there will be no net movement across them. Let's say if two are going in, two are going out. So no net movement. Now let's try to draw some conclusions. On the left side of the slide, we have this hypothetical cell 1, where the cell membrane is only permeable to K+. It is impermeable to sodium. And on the right side, we have this hypothetical cell 2, where the cell membrane is only permeable to sodium. It is impermeable to K+. Now, let's just say if all the cells in the human body at all the time are permeable to potassium, then they will have their membrane potential near the potassium equilibrium potential, that is minus 85 millivolt. But if all the cells in the human body are freely permeable to sodium at all the time, then those cells will have their membrane potential near the sodium equilibrium potential, that is plus 65 millivolt. See, what is the main difference between cell number 1 and cell number 2? Is that cell number 1 is freely permeable to potassium. So this cell number 1, it is going to achieve equilibrium potential or Nernst potential for potassium. And this cell number 2, which is only permeable to sodium, this cell will achieve equilibrium potential or Nernst potential for sodium. So any cell membrane which achieves equilibrium potential for sodium, the potential in the cell, it will be plus 65 millivolt or near that. So I hope it's clear from these hypothetical cells and how they developed certain electrical potentials across their membrane. So now when scientists actually studied the potential in normal human cells, first I think I should explain how it's done. So basically, recording is done by using two microelectrodes. See, this one and this one. One is inserted into the cell, this one, that is recording microelectrode, and the other, that is the ground electrode, is on the outer surface of the cell membrane. These both electrodes, they are attached to a meter which gives us the reading. So when scientists actually studied and recorded, they found that when cells are not electrically stimulated or when cells are in the resting state, the membrane potential was somewhere between minus 70 to minus 90 millivolt. And they called this as RMP, resting membrane potential. So what is RMP? See, this is present in almost all cells, and this is a potential difference across the cell membrane of somewhere around 80 millivolt with negative inside the cell. So most of the cells which are resting cells, because they are not electrically stimulated, only neurons and muscles got that power. Most of the cells, they have RMP of about, let's say, minus 80, minus 90, minus 70 millivolt. Now, most importantly, this RMP, look at the values carefully. Is this value close to, just a second. Yeah. So is this value close to minus 85 or is this value close to plus 65? Of course, minus 85. So RMP, which is present in almost every cell, is more near to equilibrium potential of potassium, that is minus 85. So if you look at human resting cells, they have their RMP and that is close enough to equilibrium potential of potassium and far away from equilibrium potential of sodium. Basically, they are behaving like hypothetical cell number 1. So as they are behaving like hypothetical cell number 1, it means that are most of the cells which are having RMP near minus 80 or minus 90 millivolt, their cell membrane, they are freely permeable to potassium and they are not freely permeable to sodium. That is why most of the normal human cells, they have electrical potential with a negative polarity inside the cell near the potassium equilibrium potential. Now let's just sum it up. In all human cells, point number 1, they have lot of sodium potassium ATPases and they are concentrating sodium out and potassium inside the cell. So basically all the cells, they are very rich in potassium. Point number 2, see, resting cells, they are not permeable to sodium but they are very permeable to potassium. So all human resting cells, they lose little bit of potassium. See, they have lot of potassium in but they diffuse only a little bit of potassium to develop enough diffusion potential of potassium that further potassium won't leak out, and that happens to be around minus 80 millivolt. So basically, human resting cells are allowed to achieve Nernst potential for potassium when they are rested. And this Ke flux, this small Ke flux, which is normally occurring in all resting cells, is responsible mainly for the genesis of resting membrane potential. See again, RMP is mainly produced by diffusion out of K plus, right? Or in simple words, you can say cells are basically leaky to potassium. All right, now one more thing. Let's talk about the role of sodium potassium ATPases in RMP. See, if you look at sodium potassium ATPases role in creating RMP, then it's very little, just minus 5 millivolt. Alright, so direct contribution of sodium potassium ATPases is very little out of minus 90 millivolt, that is the resting membrane potential, just minus 5 contribution. But most importantly, sodium potassium ATPases, they have a very powerful indirect role in creating RMP. And that is, see, as we say that cells are basically bags of potassium. They have lot of potassium inside. So my question is, see, who created a high concentration of potassium inside the cell? Or let's just say, who brought or accumulated the potassium inside? It's none other than sodium potassium ATPases. This was the electrogenic pump which worked actively and accumulated sodium outside the cell and potassium into the cell. So it will be right of us to say that the real role of sodium potassium ATPases is actually to maintain the high concentration of potassium inside and high concentration of sodium outside. And due to that high concentration of potassium inside the cell, that was the reason only potassium was able to leak out. So if you look at the direct contribution or the direct role of sodium potassium ATPase in RMP, it's very little. But the indirect role, they have a very powerful indirect role of concentrating these ions outside and inside respectively. So thank you so much. We are done for this video. In the next video, we are going to talk about Nernst equation and Goldman equation. Also, if you like the video, consider subscribing to the channel and like and comment. Thank you.